Okay, so there are 4 modules left in this course, but they are actually short modules. Yeah. So we look at lithography, okay, and then we would look at ion implantation and etch, okay, and then we will look at how to put all these things together to make devices and structures. Yeah, so that is the idea. What do you know about lithography? So he's saying that he want to pattern something, right? How do? It says lithography. There is no reference to light here. So if it is accomplished using light, then I'll call it photolithography. Okay. Yeah, so this is yeah, you are right. So you want to actually transfer a pattern, okay, and there are different ways to do this. For example, there is something called Damascene process. We have heard of Damascene process. You might have seen this, nice artwork where you have a wooden piece, yeah, but then metal pieces are used inside, meaning that, so you have some, I'm not a good artist, but I will give it a try, okay. So you have, let's say, meaning, yeah, so let's take something as boring as a square, right? And then I have, so this is a metal piece, meaning actually a wooden something. But then you have, let's say, something like some flower or something, okay. Not engraved, but rather this is actually made of brass. Just to give, yeah, you have seen this kind of thing, right? Yeah. So how do they do this? This is called a Damascene process. Okay. How do they do it? You can, of course, actually do a lot of things, but you cut a piece of this metal in the shape, and then etch a small, area in the wood, and then you put it in there, right? But then how do you get this perfectly smooth transition? It looks very smooth. Okay, very simple, right? You actually polish this surface. Okay, this is called the Damascene process. Very old technology. Okay, but then you can see that now it is being extensively used in VLSI, and it's called dual Damascene process. Dual Damascene. Okay. So there's a process called chemical mechanical polishing. Have you heard about this? No. Why not? We have discussed this. Anybody remember this? Chemical mechanical polish. So when we discussed about making wafers, okay, so you cut the wafer, the surface will be very rough and so on, right? So you're going to polish it using CMP, chemical mechanical polish. So go back to your crystal growth, that chapter, okay. So that is being used in, and so that's basically a polishing process, okay. But I can use that in some innovative ways to make this kind of patterns on the wafer using what is called dual Damascene process, okay. But you still need to etch. So this area has to be etched, right? And then you put the metal in, okay. So how do I actually then transfer this feature onto the wafer, right? So you have seen, this is not very difficult. As children, you might have done this kind of thing, right? You have a transparency paper, yeah, and or some mask. For example, somebody has made cuttings on cardboard, you take this and then outline this, right? This is something that you have always done, right? So why don't we do the same thing? Okay, but maybe in a slightly more sophisticated manner. Okay, so that is the whole idea of lithography. And if you look at this, right, the lithography, the litho actually refers to what? Stone. Huh? So it's kind of referring to some engravings on stones. Okay, so this technique per se is fairly old, but now how do you implement it? Okay, so you use light, electron beams, ion beams, and so on and so forth. So that is the distinguishing feature of modern technology. Okay, so lithography per se is actually not a new technique. Yeah, and we have ourselves used as kids some of these tricks ourselves, right? Okay, now this is a very important technique. You can see that, say, if you go around all this thin film deposition materials that you talk about. So these are things that, you know, if you go to many of these metallurgy, material science departments, or if you go to chemical engineering, chemistry, so they make thin films, right? Of study the properties of thin films, and then grow crystals. A lot of things are being done, but from there to actually making devices. Okay, a very important two processes. One is lithography. Okay, because all these deposition techniques allow you to put a material on the entire substrate. Okay, so that is very important. But when you want to make a device, then it is not actually, so then, you know, you have a thin film. So what is the difference between this thin film and that thin film? If both are, let's say, aluminum oxide, right? Maybe the thickness is different, but that does not give you a device, usually. Okay, so if you think of making a capacitor, very simple capacitor, right? What do you need? Two plates, yeah. But if you have, you know, a sheet of glass, for example, I want to make a capacitor. Okay, either the whole glass has to be a capacitor, right? Or I want to make small capacitors and then cut them out, right? So I should be able to then remove this capacitor is spatially limited. Okay, then I may actually say, okay, it has to be circular, it has to be rectangular, or maybe it has to be a finger type, right? Yeah, many fingers. Okay, no, so I am talking about making a structure. Yeah, it's not just deposition everywhere. Okay, or actually devices would have certain structures, right? So I should be able to selectively do processes. Okay, and one of them is to allow us to do selectively remove material, because all these thin film deposition techniques you have seen, they actually just allow you to deposit everywhere. Yeah, of course there had been some exceptions. Selective epitaxy is one of them, but most of the cases, most of the other cases that we have seen are just you are depositing everywhere. Okay, so lithography is a very important thing which gives you selectivity. Okay, so now there are two aspects to it. One is related to meaning of, we actually, you know, in the beginning of the course I said that in VLSI technology you do two things. One is to add, okay, so additive processes, and then the other is subtractive processes. Okay, now lithography brings in spatial selectivity in both. Yeah, so you can see the additive process which is directly related to lithography is actually ion implantation. Okay, so you what we are talking about is you actually have a wafer, like I want to let's say I want to make N-channel MOSFETs in some regions, P-channel MOSFETs in some other regions. Okay. So wherever I want to make N-channel MOSFET, it should be, what should be the doping of the silicon? N-channel P-type. So it has to be boron, and in the regions where you want to make P-channel transistors, it should be N-type. Okay. So I should be then selectively doping these regions. Okay. So one of the technique that is used is ion implantation. How do you get the selectivity? You need to mask. Okay. So how do you create the mask? On the wafer? Photolithography. Yeah. So we'll see this in more detail. Now, second thing is, whenever you're doing thin film depositions, it is usually everywhere, right? The film gets deposited everywhere. So you now need to remove this selectively, yeah, from certain regions, and then you would actually create this pattern using lithography, and then remove the material again from regions where you don't want the material. Okay. So lithography provides you a mask on the wafer. Okay. You are actually putting a mask on the substrate. That is what lithography does. Okay. So we'll see this process in some detail. And as I mentioned, this is very, very important for making any electronic device. Okay. So what distinguishes a lab where people make electronic devices and, let's say, a thin film lab is most of the time the lithography tool. Okay. So the basic lithography process is shown here. So what you actually want is some features on the wafer. Okay. So let's say this is my wafer surface. I'm drawing this as a rectangle. Okay. So I say that, okay, I need a P-channel MOSFET here and an N-channel MOSFET here, right? And so on and so forth. So I have some patterns on this. So I actually need some method to draw all these features. Okay? At least have a conceptual design. Yeah? I should lay out these things on something. So these days we use computers to do this, right? So you actually create these patterns, and then so this is called layout. You create a layout of what you want on the wafer. Okay. And then there is, of course, you create this layout, yeah. And so I said that this is an N-channel MOSFET, this is a P-channel MOSFET, and so on and so forth. And then I will actually make, you have done this PCB design, right? PCB design, PCB layout. Anybody? Printed circuit boards. Same thing, right? You want there, of course, you have this resistors, transistors, capacitors, and other elements. Now you are actually trying to draw how they are being connected between different layers in a PCB. Okay, something similar. Then after this thing is made, the layout is made, you would really like to know whether the final device and the circuit would work. Okay, and there may be certain constraints introduced by technology, right? So these are called design rules. Okay, whether you have violated any design rule. Okay, this is what you do in part of the VLSI circuit design is actually the layout. Yeah, making the layout, and where there are design rules which says that this pattern has to be away from the next one by a certain distance. You can't violate this. Okay, so you actually do simulations to see whether the thing that you have designed actually conform to the design rules. Okay, and the next thing is, of course, I can extract a circuit diagram from this layout. Yeah, because I have a transistor, right? This actually represents a transistor. Okay. Then see whether the eventual circuit would work. Yeah. So you have all this design rule checking and the simulation of to see whether the IC or whatever circuits you're making would actually work. So next thing is you have this layout that has been tested, at least on your computer, and you have some confidence that it is going to work. Okay. And then you do what is called a tape out. What it means is that after all this testing, you have these files which actually describe how you lay out the features on your wafer, and then you need to make what is called a mask. Okay. Yeah. So this mask is not the mask on your wafer. Okay. This would be typically made on glass if you are talking about photolithography. Okay. So because glass is transparent, yeah. So I take a mask, a glass piece, so it is transparent, right? And then I coat this with an opaque material by using thin film deposition techniques. So I can, for example, deposit chrome, the very common material used as, meaning an opaque thing on the glass for lithography. Or you can also make iron oxide. Okay. So what am I trying to do? I would really like to have this feature on my wafer. Okay. And I say, okay, this region should be opaque. Yeah. So we'll see how to actually determine this later on. Okay. So I want this region to be opaque, this region to be transparent. Okay. So what am I actually saying? That now I have a glass plate where the opaque material is everywhere on the glass. Okay. So I should retain it here, the opaque material, let's say chrome, and remove the chrome from these areas. Okay. So that is part of the layout that I have got. Now how do I get this onto a mask? Okay. So now, if for a simple lithography system, you can actually make this mask using transparency film. You have seen these transparencies, right? A plastic sheet, somewhat thick, okay, maybe a millimeter or so thick, plastic sheets, and then you can print using your normal printers, right, on the transparency sheet. Okay. So if the feature size is more than 20 micrometers, you can actually get these features printed on a transparency sheet. Okay. You don't have to go and buy this glass with chrome coated on it, very expensive. Yeah. Instead, you go to Andheri, for example, there are many companies that actually will print transparencies and give to you. So you make a design. If I want to make a cheap sensor, right, where the feature size are 100 microns in that range, I don't have to go for all this expensive mask making process. I just go to, I've designed this maybe even in PowerPoint, right, yeah, because we are talking about features that are fairly large, 0.1 mm. So I make these features, lay them out, and then get it printed on a transparency. I can use it in a photolithography system. Because transparency is transparent, right? Now you are printing black ink in regions where you want to block the light. Okay. So you have very simple mask. Okay. But here it goes a little bit more sophisticated. So you are going to use an electron gun, an electron beam, okay? And an electron beam can be focused into very, very narrow spot, yeah, by providing sufficient acceleration or energy to the electrons. Okay. Now the advantage here is that you have an electron beam, so I can focus it very well. Okay. I can steer it by using electric and magnetic fields. So what am I going to do? I actually take this glass, I have the chrome on it, right? And then I spin coat, okay, what is called an electron beam resist, okay, electron beam sensitive resist. So this resist is a chemical, yeah, a mixture, okay, and depending on whether I use an electron beam or a light, okay, this chemical would be sensitive to electron beam or photons, okay. So what happens in this case is that the chemical would actually go through some transformations, typically polymerization reactions, or maybe some polymers will be broken down. So there are different types of resist, and I'm going to expose. So I actually have this photoresist deposited on the entire glass plate, okay, yeah. So on the side where you have the chrome, right, or iron oxide, you actually deposit the resist. Resist is very simple to, so it is actually a fairly high viscosity liquid, like good quality honey, right. So you drop this on the center of this plate, and then you spin the plate at very high speeds, okay, 10,000 RPM and so on, yeah? Typical numbers. Yeah? I spin this very fast, so this would actually spread. Huh? The photoresist would, or in this case electron beam resist, would spread on the wafer, okay. So you can get fairly good uniformity or uniform thickness of this resist on the wafer, and then you would bake it at temperatures around 100 degrees centigrade. Bake means what? You're actually getting rid of some of the solvents in the photoresist, so it actually does not flow any further, okay. Otherwise, if I take this, right, if it's a fluid, right, highly viscous fluid, so I take this and hold it like this, it will slowly drip down, right. So I need to actually, I'll do a baking, right, so it becomes a solid mass on the wafer surface. And then you are writing on the electron beam resist using this electron beam, focused electron beam, okay. So this would then, the resist would undergo certain chemical reactions, okay. And there are two types of resist, so that we will see later on. And then you can selectively remove the resist from certain regions, okay. So usually, let's say that wherever you have exposed the resist to electron beam, you can remove that region very easily by just dipping this glass plate in a chemical called developer, okay. So if you are familiar with photography, not the kind that you do with your mobile phone, yeah, but maybe you have not seen this, right. So we used to have this cameras with film, film rolls, where exactly same thing happens. Yeah? So you have some photosensitive material on the on a plastic roll, right? And then you are exposing it to light, and then you go and take it to a dark room and develop it. Same process, okay? So you are developing it. Essentially, you are etching out the photoresist, or in this case, electron beam resist, from regions which is either exposed or not exposed to electron beam. So we will see that difference later on. So you have transferred the layout that you made here, yeah, with the features onto the glass plate. So you have glass, okay, and you had this chrome, yeah, opaque substance on the entire glass surface, one side of the glass surface, meaning one side of the glass, and then you made these patterns by this process that I just mentioned. So I have this thing, I now take this to the photolithography system, okay, and I have some optical arrangement. So I have a light source, okay, and then I have what is called a condenser lens. So we'll see this some variations of this, and I keep the mask here. Okay, this is one scheme of how you do it, and then you have another lens. Okay, so you pass the light through this, right? So the light will pass through the areas that are not, meaning that are transparent, right? So not through the entire thing. So it goes through, and then you are doing something here to maybe reduce the size of the image and so on. So we'll discuss that later. And here you have wafer on which you have again spin coated photosensitive resist. Okay. So in this case we used a resist that is sensitive to electron beams. Yeah. Here we would use a resist that is sensitive to photons. Okay. So you do this. Now you may ask, so I actually do this exposure, I shine light, it goes through the mask and then falls on this photoresist, right? So some areas on the photoresist will actually see the light, yeah, because you have some mask, yeah, the light will not go through onto the entire wafer surface, right? Will actually, so the light will not go through these regions, for example, right? Yeah. So this, an imprint of this would be actually obtained on the wafer. Okay. So I can take this again, I would develop this wafer, yeah, or the photoresist by dipping it in some developer. It's again some chemical solution, and I can use it further. Okay. Now you may ask this question that we actually are making a mask, okay, on the wafer, okay. But for that we may already made a mask here. Yeah. So why don't I just keep this part, I take this wafer, put it here, right? So I have the computer directly connected to my electron beam lithography system. I don't have to go through all this mask making, glass and all business, right? I directly write. So this is called a direct write lithography. Okay. So you are actually, there is no mask as such here. Yeah. So you have a computer generated pattern. So the electron beam lithography systems would have what is called a pattern generator. Okay. Pattern generator. And that just generate the pattern and deflect this beam. Okay. And you may actually have an XY stage for this mask, this plate here. So it is moved in X and Y. And small deflections can be achieved using this plates where you apply electric fields. Okay. So this can be all modulated or controlled by the computer based on the layout that you have created. So why do we need this in the first place? Pardon? Small? Yeah, she is saying small feature sizes. You saying something? Why not? There also I can just, once I do the design, right? It stays in my computer. Okay, okay. So, yeah, what he is saying is that this would take a lot of time. Because you have an electron beam, it has to be scanned line by line. Okay. So, making a mask, complex mask can take several hours. Okay, on a single wafer. But if you, or maybe even days, depends on the system capabilities. But this one is very easy. It's just shining light once, right? So this actually goes in few seconds. Okay, so the throughput here is very, very large compared to this, yeah, which is a very important consideration in manufacturing. Okay. So photolithography systems have very high throughput. Electron beam lithography actually though is very precise, and you can really make extremely small features because what limits the dimensions of what you finally print on the wafer is determined by the wavelength of whatever you use for excitation. Okay. So electron beam, the electron wavelength can be reduced by just accelerating the electrons. Okay. So they have higher energy, smaller wavelength. But here that's not possible, but the good thing here is that the throughput is very large. Okay. Now this is now once you have this mask, this is what you do. This is one example. So you have a silicon wafer with silicon dioxide you obtained by using thermal oxidation, and then you apply photoresist on top. Okay, spin coat photoresist, and then you have this photo mask. You can see the glass piece transparent, but on this face, the bottom face of it, you have this chrome pattern remaining on the wafer. So when you shine light, okay, so this region is masked, which means that the light would actually fall on this white areas, not the shaded areas, right? So in this particular case, you develop it. So what you do is you take this and put it in this chemical solution called developer. So in this particular embodiment, what is happening is that the photoresist that is not exposed to light etches out very easily, not exposed to light. Okay, so this is called a negative photoresist. Negative photoresist. Okay, the resist regions that are not exposed to light can be etched out in the developer. So this is called a negative photoresist. The opposite is positive photoresist, where the regions that are exposed to light would dissolve in the developer. Okay. Now I have the silicon dioxide exposed in this window, right, in the photoresist. So I can actually dip this in a solution or a chemical solution which would etch the silicon dioxide but should not etch the photoresist. Okay. So you can use what is called buffered HF for doing this. Okay. And you can etch out the silicon dioxide in this region. And then subsequently the photoresist has to be removed. So usually this photoresist contain organic compounds, right? So you can remove this in organic solvents like acetone, isopropanol, and so on. Okay. So you remove this photoresist or some organic solvents like sodium, potassium hydroxide, and so on and so forth. Okay. So you can remove this and you get this pattern on the silicon dioxide. Okay. So I can do further processing here. For example, I can do an ion implantation. So the silicon dioxide on the surface act as a mask for ion implantation, right? You can actually implant only in this region. Okay. So that is the basic idea. So we'll discuss it further in the next lecture.